Good morning. We will pick up where we left off. Today we're basically working a lot of problems and getting ready for tomorrow's exam. I also have some demonstrations to show you that for some reason I couldn't show you last time, but I've got several of those. All right, so last time we ended up by finding the rotational inertia for several of these objects about the given axis of rotation. And now the next step here, we're going to find the torque from gravity. So these T's, in case you're wondering, they are being held horizontally. We are looking down from the top. They're being held horizontally. And if you were to let go of them at that instant, we want to know what is the torque on them due to the force of gravity, due to their weight. So we're going to do just the same three we did last time. A, we'll do A, D, and E. Let's see, did we not do E? Oh, you're right. You are correct. Thank you. Let's do that. Let's start off. We did last time. We did A and D. We didn't quite get to E. Let's do that. How are we doing? We done? Object 1 is just a rod, right, rotating about its end point, 1/3 ml squared. Object 2 is a rod. I found better props today. A rod rotating about this point, right? So the axis of rotation is also the rod. So all the mass is on the axis of rotation. It has no rotational inertia, 0. Add them up. Okay. Now we'll find the torque due to gravity for each one. Torque from gravity. What do we care about? The center of mass. Center of mass. These objects are just being released from rest. And we will know what the acceleration is in a minute. Let's not get ahead of ourselves. That's the next thing we're going to find. So what do? We can replace this object with a massless object and a weight hanging at the center of mass equal to the mass of the object, right? So the center of mass of rod 2 is there, and the center of mass of rod 1 is there. Or you could find the center of mass of the whole system if you wanted to, but I think this is easier. But whatever you prefer. I guess since they're both the same mass, it's finding the center of mass of the system is just as easy. If they were different masses, then I think treating them as separate rods would be easier. But either way, it's the same thing. All right, so the torque is the force. The force is straight down into the page. The lever arm is this distance right here. So this is the force times the lever arm. The force is the weight. The lever arm is L over 2. We do the same thing for the other one. And we add them up. Because they're in the same direction, we can add them. It's vector addition. We good with this one? Okay, how about D? D, we have 1, 2, 3, 4. Oops, a little too far. Force is just the weight of gravity, yeah. We've got this rod here, basically, right, hanging off that from the axis of rotation, and we're holding it. It's horizontal. We're holding it, and we're gonna let go, and gravity is gonna cause it to start rotating, right? Gravity is gonna produce a torque, which causes it to start rotating. That's what we're trying to find here. Okay. The first one experiences no torque because the force of gravity is pulling down right at the axis of rotation. Here's the rod. The axis of rotation is in the center. Force of gravity is pulling down right at the axis of rotation. It can't get it to rotate at all. Produces no torque. The second one we've already sort of done above there. It's mg times the lever arm, L over 2. And add them up and you get 1/2 mgl. And E is this one. All right. Good with this one? Now, what are we going to do? We're going to put it all together, right? Yeah, perpendicular distance from the line of the force to the axis of rotation. That's correct. The torque from one is no, we're talking force times lever arm. The force is the force of gravity, mg. And the lever arm is L over 2. It's right there, right? It's being the force of gravity is down into the page, and the lever arm is this distance right here. Alpha should have direction here, you're right. Let's just find the magnitude, how about? Well, we could look at each picture. Where are the pictures? So for A, what's the direction of alpha? It has to point, remember, it has to point along the axis of rotation. So if this object would fall down towards the right as we're looking at it, the axis of rotation is here. Right? There's the axis of rotation. So alpha would have to point which way? Alpha would have to point toward the top of the page. How about D? If we release this thing, this is a top view, yeah. This side is going to go down. So alpha would point along the axis of rotation. We've got a 50-50 chance to the right. I could put vectors on these then. Oops. So let's take a look at the end view. Where's A? A is, if we look at A, what do I call it? Side view. Here's our axis of rotation. There's our T hanging off of it. And what's going to happen? It's going to rotate this way when we let go of it, right? We put our thumb on the right, from our right hand, put our thumb along the axis of rotation. And if our fingers go in the direction it would rotate, the direction, that's the torque. The torque is in that direction. So if the torque would cause this thing to rotate, what are we, clockwise as we look at it? We put our thumb in the direction of along the axis of rotation such that the fingers on our right hand go in that direction. So it's either into the page or out of the page in this, for this drawing I just have here. If it was out of the page, the rod would rotate counterclockwise, but it's rotating clockwise. So my thumb has to be pointing along the axis of rotation into the page. That's for the torque. And alpha points in the same direction as the net torque, right? That's how it gets its direction. So alpha would be into the page. If you're looking at this picture, into the page, if you're looking along the axis of rotation. But we're not looking at this picture, we're looking at the top view. We're looking down from the top. So when we're looking down from the top, we say the rod is going to rotate this way. So we put our thumb in the direction along the axis of rotation, which is along the dotted line, such that our fingers on our right hand roll in the direction the object would rotate. Did that help? We could do one more. Where's let's do D. We could do D also. So here's our axis of rotation. If we're looking, where's D? D. If we're looking down the axis of rotation from this side, we're looking from this side at the axis of rotation, then the extra weight is over here, right? The extra has an extra part on this side. So how is this going to rotate? The torque is causing it to rotate in this direction. There's extra weight on the left-hand side if we're looking down the axis of rotation like this. We put our thumb along the axis of rotation, so it would point out of the page. So this one, and this one, the torque is out of the page. Alpha, same direction as the torque. All right, so if we swing around and look at it like this, alpha points that way. And E, it's going to point along the axis of rotation. We've got a 50-50 chance. It is to the left. Because when you put your right hand with your thumb pointing to the left, what do your right fingers do? They fold down into the page. And what would this object do? It would roll down. It would start to rotate down into the page. So that's the direction it would go. Okay. All right, I wanted to show you, we have this, we use this all the time, right? How do we get back and forth between translational variables and rotational variables? We use our S is equal to R theta, V is R omega, A is R alpha. I wanted to show you an example of this. As you move farther out, every point on a rigid object rotates with the same speed, with the same angular speed, right? The same number of revolutions per second or whatever it is. But as you move farther and farther out, you have to move faster and faster and faster to keep up, right? Let's see, last question, or no, another question here for E. E, the axis of rotation for E is here. So if you let go of this thing for horizontal direction, this part is going to fall into the page, right? It's going to roll over in that direction. It's going to go down into the page. Then you put your thumb along the axis of rotation such that the fingers on your right hand this is a top-down view. We're looking down on these objects, right? So if I have a rod, my arm is the axis of rotation. I have a rod connected to it. I'm looking down. If I was looking down from the top and I let go of the rod, what would happen? It would go down away from me if I'm looking down from the top, right? So this is a top-down view. So E is going to go into the page. When I let go of it, it's going to roll down into the page. You see that now? If you're okay, let's rotate this by 90 degrees. So you're looking down at this. Gravity's pulling away from the camera toward me. I let go of this rod. What's it going to do? It's going to come toward me, away from the camera. Toward me, away from the camera. So what do? You put your thumb along the axis of rotation, either up or down, right? You have a 50-50 chance. If you put your thumb down, the fingers on your right hand roll away from the camera toward me. My fingers do, right? So that's the direction this thing would go if you were looking down on it. So the alpha, the torque and alpha would be pointing down, down being that way. It's probably a good idea to practice shifting by 90 degrees, looking at something one way, like this is a top view, and then rotate at 90 degrees, look at it again and see what it looks like in that orientation. Okay, let me show you an example of this. V equals R omega. These 2 meter sticks represent railroad tracks. If train wheels were cylindrical, they wouldn't stay on the tracks very well. Any slight deviation from being centered, and they roll right off. But if they have a conical shape to them, which they do, they look sort of like this. Now I've removed the axle and just sandwiched the 2 wheels right together. But that's the shape they have. They're smaller diameter on the outside and larger on the center. Watch how these steer towards the center of the track. One more time, I'll make it a little more obvious. Now let's watch in slow motion. Okay, so you see what's happening there. So you've got your train wheels look something like this. Right? That's what they look like. I just took the axle out and put the two cups together. Same thing, right? Same thing. Your tracks are over here. Let's say, the train veers a little off to one side. So on one wheel, it's making contact over here. Right? On one wheel, it's making contact over here. And on the other wheel, it's making contact over here because the train is veering off a little bit to one side. It's moving off to the right here as we're looking at it. If the train was moving away from us, it would be veering off to the right. So the way these train wheels work, it's not like the wheels on your car that rotate independently. They are rigidly attached together. They all rotate together at the same rate. So that means that this part right here, the red stripe on the left wheel, does not have the same tangential speed as the red stripe on the other wheel. The one on the right has a faster tangential speed, right? A bigger V. They all have the same omega, but the radius is bigger, so it has a bigger V, so that it covers more distance. That red stripe covers more distance in the same amount of time, which means it's going to steer the train tracks toward the left because it's going to cover a little bit more distance than the one on the other side does. In the same amount of time, it's going to steer the wheels toward the center. And so the wheels will always be steering themselves toward the center of the track because of that shape. All right. Yes. Right. Both wheels and the axle are all welded together, so they all move as one unit. The omega is the same for everything, but the bigger the radius is along that conical shape, the bigger the translational speed. Omega is the same for every point on a rigid object, any rigid object. So if I have if I have this object and it's spinning with some omega, it doesn't matter where I am. I could be over here, I could be out here, I could be on the rim. It doesn't matter where I am on this object. Every point has the same omega, right? Every point moves the same angle in the same amount of time. Any rigid object. It could be a rod, right, rotating. Every point on this rod has the same omega as it rotates. Any rigid object, every point has the same omega. All right, let's do one more while we're at it here. Everybody knows things roll downhill. I don't have to demonstrate that for you. But let's take a closer look at what causes rotation. This L-shaped object topples over and won't stand up straight on a horizontal surface. But put it on an incline, and it stands just fine. Let's take a closer look at why that is. This object has an arrow suspended from its center of mass. Gravity pulls it towards the center of the Earth. Take a close look at where that arrow is with respect to the support base. There's the arrow, and there's the support base, and this object is standing up straight. Where is it in this case? What's going to happen? Put it on an incline, and notice where the arrow is now with regard to the support base. Here's a demonstration you may have seen done with a wine bottle. But since I'm shooting all these video demonstrations at home because of COVID-19, I thought this was more appropriate. Where is the center of mass of the bottle? Let's take another look at my disc. Where is the center of mass of my disc? It's not in the center. Okay, let's go through this again. Some good stuff in here. So, why do objects typically roll downhill? I'm going to try to annotate on this thing. We'll see. Let's see. What color do I need? Red. Okay, where's our axis of rotation? It's right here, right? That's the pivot point. The point of contact with the wheel and the ground, the ball and the ground, whatever it is. Actually, let me move that over just a little bit. It's right here, right? It's the point that makes contact with the ground. Most objects, where's the center of mass? It's at the center of the object, maybe here. So if I draw a line, can I draw a line with this thing? From the center of mass, right, towards the center of the Earth, straight down, that's the force of gravity is pulling along that line. The axis of rotation is to the left of that line, so we get torque. And what direction is the torque? That way. So most objects roll downhill. The center of mass is at the center of the object. The pivot point, the axis of rotation, is off center because it's not sitting on a horizontal surface anymore. That creates torque, and it rolls downhill. We okay with that? Now, where's the center of mass of my object? It's not at the center. It has to be on the uphill side of the center. It has to be over here. So I draw a line. Gravity pulls at the center of mass, right? Gravity pulls straight down here. And the pivot point, the axis of rotation, is on the right side. So now where's the torque? The torque is in this direction, and my object rolled uphill, at least for half a revolution. It's not going to keep rolling uphill. roll downhill. I don't have to demonstrate that for you. But let's take a closer look at what causes rotation. Okay, how about this guy? This L-shaped object topples over and won't stand up straight on a horizontal surface. But put it on an incline, and it stands just. All right, so let's take a look at this one. Where's my... Where's the center of mass of this object? Over here, right? Somewhere, right about there. If I draw a line straight down towards the center of the Earth, it's within the support base, right? So the base of this goes from here to here. If that line, if the force of gravity, if I draw that line, force of gravity comes down within the support base, it produces no torque. The object doesn't roll over. But if I have that object standing here, here's the center of mass. Force of gravity pulls down on it. Here's the edge. That becomes the axis of rotation, right? And I get torque. Well, that wasn't bad with the mouse. Okay. We all right with that one? It's fine. Let's take a closer look at why that is. This object has an... So this is nice because it shows us where gravity's put. It has the line already drawn on it for us, right? That white arrow always points toward the center of the Earth, and it's pinned at the center of mass of our object. So as long as it comes down within the support base of the material, arrow suspended from its center of mass, it will be a nice stable. Gravity pulls it towards the center of the Earth. Nice stable setting. So right here, we draw a line down from the center of mass towards the center of the Earth. That's what the white arrow is showing us. And obviously it's within the support base. This object doesn't rotate. It just stays like that. And if we flip it around, same thing, right? Take a close look at where that arrow is with respect to the support base. Now here, the arrow, of course, is right here. The support base is from there to there. So the arrow is coming down within the support base. It produces no torque. Same here. It doesn't topple over. There's no the arrow, torque. And there's the support base. And this object is standing up straight. But now, where's my erase? Let me get rid of those other marks. The support base starts here and goes over to here. But where's my arrow pointing down? Okay, you get the idea. Over here, not within the support base. So what's going to happen to this guy? Where is it in this case? There's torque. What's going to happen? It's going to rotate to the right. Excellent. Put it on an incline. And notice where the arrow is now with regard to the support base. Okay, so now the arrow comes down here, but the support base starts out here. It's within the support base, no torque. Okay.
Here's a demonstration you may have seen done with a wine bottle. But since I'm shooting all these video demonstrations at home,
Okay, so where does the center of mass have to be? Has to be somewhere between here and here. Otherwise, there's going to be torque. Center of mass is probably right around there. Okay. All right, let's do, I guess it's time for a break. Let's take a 10-minute break. Then I've got another problem for you. That's the problem. Thank you. Like, why is nobody responding to me? Okay. Office hours. Questions about office hours. So my 4 o'clock office hour, I'll do that, but I often get a lot of 4B students. So if I start early, should we start one just specifically for 4A this afternoon at like 3 or 3:30? Sounds good. Okay. So use the normal 4 o'clock office hour login, but I'll start it early, like what time's good? 3:30? I have another class before this one tomorrow. I could do something late tonight. You want an office hour late? 10:30? All right. Well, so let's do this. Let's plan on 3:30, and then I'll see if I can do. I'll send out an email with a link for one if we do one later tonight. I'll try to do that. Okay. So 3:30, better write this down. 3:30, and then maybe something later. Okay, sounds good. What I'll do is I'll definitely post the notes. If we work we'll probably be working problems mostly. So I'll post the notes next to in the lecture notes area. I'll post those so that you'll at least see all the solutions for everything we work. Okay, let's do this problem. Let's do an energy problem, and then we'll do start with this one. Okay, we've got our favorite shaped object here for the day. And it's released from rest, and at some later time, it is toppling over through horizontal there as it's passing through horizontal. So let's treat each of these given. That this is L and M and M and L. Find omega final. It has to be so this is what we call unstable equilibrium. Right? Could the object be in equilibrium like that? Technically, yes, right? There is a point where the center of mass of our object is exactly over the pivot point, and at that exact point we get no torque, right? No force, no torque, no net force, no net torque. The object is technically stable there. But any tiny deviation, if it moves 1/10 of a millimeter in one direction, what's going to happen? It's going to rotate over. So that's called unstable equilibrium. The example we like to use is if you have a bowl and you put a marble inside the bowl there. This is stable equilibrium because if you displace the marble a little bit in one direction, what direction is the force on the marble? Back toward equilibrium. If you displace it the other direction, what direction is the force? Back toward equilibrium. So the marble is always being pushed back towards its equilibrium position. Equilibrium means the sum of the forces is zero, right? Same here. If we turn the bowl upside down and put the marble on there, technically there's a point there where we could balance that marble. Technically. But any tiny little deviation from that, and what direction is the force? away from equilibrium. That marble slides away from equilibrium. So this we call unstable equilibrium, and the other one we call stable. So we'll assume that this object is just a tiny bit off from equilibrium. Okay? So what's a good way to solve this problem? Energy. No friction, no air resistance. We will, all the initial energy is gravitational potential energy. And at the end, what do we have? Rotational kinetic. You could do this too. You could treat each rod sort of individually, or you can find the center of mass of the system, whichever you prefer. If you would like to, we could do the center of mass of the system. The center of mass of the system is halfway between here and here, right? So it's at 3/4 L. Or you can just do the two individual rods, whichever you prefer. So this is going to be MGH. M is 2M. MGH. The mass is 2M. G is G. The height is 3/4 L. That's our gravitational potential energy. And at the end, we have 1/2 I omega squared. And we could number these and come up with the rotational inertia. I1, we use our parallel axis theorem for it. We okay with this one? We've got our object rotating about, that's the center of mass. Oops. That's the center of mass axis would be over here. So D would be that distance right there. No, you cannot do that. Question about the height for gravity. The height is the change in height of the center of mass. That's a good point I should have made. The center of mass ends up, what color am I going to use here? Green. The center of mass ends up over here. And it starts out over here. So what is h? H is the distance between those two, right? Let me go with green. You're finding out how much the center of mass drops in this problem. Then it says, for I1, can we make the rod into a point mass at the center of mass and calculate inertia? No, because what you end up with is only this part, right? Only the second part that from the parallaxis theorem. You're not going to end up with this part then. So that's not the same thing. For the only time we can use center of mass pretty much is for gravity, gravitational potential energy, and torque due to gravitational force. For those cases, we can take our object and make it a point object at the center of mass. But no other case can we do that. Definitely not for rotational inertia. The one example that's really clear about that is like a disk rotating about its center point. What's the rotational inertia? It's not zero, right? It's 1/2 mr squared, a solid disk rotating about center point. Well, if we took that disk and replaced it with a mass at the center of mass, it would be zero. I would be zero, right? Because all the mass would be on the axis of rotation. So that's one of those examples that jumps out at you. If you no. This is side view. This is a side view. Gravity here. Gravity is this way. This is a side view. There, does that help? Sorry about that. Side view. If you treat each rod separately, the height for one of the rods will be L/2. The height for the other one will be L. And by the time you add them together, you get this. Oh, yeah, we're here. So we've got a rod. We've got a rod 1 rotating like this. Here's an axis of rotation, and the rod is doing this, right? So we don't have anything like that in the formula sheet, but we have a rod parallel. We could find an axis parallel to the one that we know, the one of interest, that passes through the center of mass of the rod. Okay, that gives us 1/12 ml squared. And then the distance between the center of mass and the axis of interest is what I labeled D here. So we do the center of mass rotational inertia, the axis through the center of mass, 1/12 ml squared. We add to that the total mass of the object times the distance between the two axes squared, the center of mass and the axis that we are interested in. And in this case, it's the length of one of the rods. Good with that? Let's finish I here, and then we'll go back, look at the other things. I2 is just a rod rotating about its endpoint. You see that? One-third ml squared. What is that? 17/12. All right, let's go back. A couple of questions. So we could do this. We could do you've got an mg L over 2 plus mgl What happened? Uh-oh. Uh-oh. Come on. I think it's crashing. It's trying to decide whether it's going to crash or whether it's going to recover. Come on, make up your mind. It decided. It crashed. Share. There we go. I think we're back. Oh, I've got to bring my chat box back. Okay, there we go. We're back. Two separate rods, or use center of mass. And when we do the center of mass, we can do, where's my, there we go. We treat them like point objects, right? So we have, if this is x equals 0 or y equals 0 here, then this would be m, and this would be m, and this would be y equals L over 2, and this would be y equals L. M times L over 2 plus M times L all over 2M. And what do we get? We get 3L over 4. And then we put all the mass at that location. Okay, maybe that's better. All right, good review there. Let's finish this one off. We've got our energy, gravitational energy, 3/2 mgl. Is equal to 1/2 I, which we just found, omega squared. Whatever that is, 36/17, something along those lines. If you're doing two separate masses, so what I do, yeah, I only do the two separate masses for the, I mean, I guess you could do it two separate rotational energies too. Yeah, sure. I didn't think of that. When I have something rotating, I just always think of it as one object. And then when I find I add up the I for each part of the object if I have to kind of break it into multiple parts for that. But you could have just said 1/2 I1 omega squared plus 1/2 I2 omega squared. Sure. I guess you could have done that. That would work. We're only treating it like a point mass for gravitational potential energy. On the left side of this equation, we're treating it like a point mass for gravitational potential energy. On the right side, we are not treating it like a point mass, cannot do that for energy or I or anything like that. The only two cases you can treat it like a point mass, gravitational potential energy and gravitational torque. Torque caused by gravity. Good? Why? Well, the simplest example for why you cannot use center of mass for I. Think of a disk rotating about its center point. Okay, a disk rotating about its center point has rotational inertia because some of the mass is away from the axis of rotation. 1/2 m r squared, rotational inertia for a disk. But if you take that disk and you put all its mass at the center of mass, what would the rotational inertia be? 0. It's not 0, right? Think about a rod rotating about its midpoint here. 1/12 ml squared. But if you took the mass of the rod and put it at the center of mass and tried to find I, what would it be? 0. You can't use center of mass for I, for rotational inertia. Yeah, you add up the mr squareds for the little ones. That's right. But you're not moving them. You're not moving them to the center of mass. You're leaving each one exactly where it is and adding up the mr squareds. You're not moving them to the location of the center of mass and then adding them up. That's the difference. No, no way, no how. You cannot do that. We have two parts to this problem. Gravitational potential energy is half of the problem. That's our initial energy, is gravitational potential energy. How do we do that? Well, we look and see how much the center of mass changed. How much height did the center of mass gain or lose from the beginning to the end of the problem? And that tells us how much gravitational potential energy it had at the beginning, because the center of mass is lower at the end of the problem than it was at the beginning. So we're going to use center of mass for that. The second part of the problem, we have something rotating. We have kinetic energy, rotational kinetic energy. We cannot use center of mass for that. We have to use another technique. We have to use the shape of the object. Definitely has a big effect on what its rotational kinetic energy is at the end of the problem. We can't just put all the mass in one location. But for gravitational potential energy, the shape of the object doesn't matter. All that matters is the center of mass changed by a certain height. So if you just remember that only two times we can replace an object with a point object at its center of mass are gravitational potential energy and gravitational torque, right? The torque caused by gravity. Those are the only two times we can do that. All right. All right, let's do. Oh, actually, I've got another video for you. Torque.
Here I have a spool, or a wheel.
Okay, here we go.
Here I have a spool, or a wheel, with a ribbon wrapped around the axle. I'm going to orient it with the ribbon coming off the top of the axle, and I'm going to pull it like this. Pause the video and predict what's going to happen.
Okay. What's going to happen when I pull on that wheel? Okay, we good with that? We pull on this, it's going to rotate clockwise and move to the right. Good.
Now I'll orient it slightly differently so the ribbon comes off the bottom of the axle. Pause the video and predict what's going to happen when I pull the ribbon.
Okay, should we see? Okay, why is that?
Now I still have the ribbon coming off the bottom of the axle, but I'm going to pull at an angle.
All right, in the first case, we were pulling here, right? Forget about this one. First case, we were pulling here. The axis of rotation, where's the axis of rotation? It's right there. You see that? Where it's touching the ground. So where's the torque? Torque is this way, right? I wonder if my pen will work here. Oh, my pen works. Now, this case, my force is this way. Where's the axis of rotation? I know a lot of you are thinking it's the center of the wheel, right? But it's not the center of the wheel. The pivot point is here, right, where it's touching the table. If it was the center of the wheel, yeah, the wheel would go counterclockwise, but it's not the center of the wheel. It's where it's touching the ground. So the torque is still in the same direction. We get the same result either way, whether it comes off the top of the spool or the bottom. We good with that? Well, let's see. Let's see if we're good with that.
Still have the ribbon coming off the bottom of the axle, but I'm going to pull at an angle, like this. Pause the video and predict what's going to happen.
Where's the axis of rotation? Axis of rotation is right here. How do we determine the torque? We follow a line back here, right? If we extend this line back, we can determine the torque. What's the torque in this case? Zero. This force can't cause that to rotate if it's applied just right. Should we see how good I am at applying that force? It's supposed to go through the axis of rotation. Okay. We good with this one? Okay, how about, what do I want to do next? I've got a, let's do this one.
This hollow hoop has all of its mass
Oh, question about the previous one. Pull it straight up. Oh, then you're going to have torque. Then it'll rotate counter. Which side is it on? If we're pulling on, hold on. If we have a, if this is touching the ground and we're pulling here, the pivot point is over here, right? So you got torque this way. So it'll roll counterclockwise then. Good. Just extend the line of force. Look at the pivot point, the axis of rotation, and see where the torque is. Okay, now here we've got this situation.
Hoop has all of its mass concentrated at its rim. It has the same mass and radius as this solid disk, but the solid disk's mass is uniformly distributed throughout the volume. Pause the video and predict which one has the greater rotational inertia.
Which one has the greater rotational inertia? The hollow hoop. All of the mass is far away from the axis of rotation, whereas the other one, some of the mass is far away, some is in the middle, some is close. If you look them up on the formula sheet, you see one of these has actually twice the rotational inertia of the other one.
Now we're going to have a race. Pause the video and predict which one will get to the bottom first.
Place your bets, yeah. It's 462-0, but we're rooting for the underdog this year. Let's see. Okay. The one with less rotational inertia, because as they roll down the hill, they both started with the same amount of energy, right? They both had the same mass at the same height. They both had the same gravitational potential energy. So as they moved down the hill at any height, they had to have the same energy. When they got to the same height, they have to have the same energy. The one with more rotational inertia is going to have more of its energy in rotational energy than in translational energy. It's going to split. The kinetic energy is going to split between rotational and translational, right? So the bigger I is, the bigger the inertia is, the bigger the percentage as it's moving down the hill, the bigger the percentage of that kinetic energy will be in rotational kinetic energy, not translational. So the one with the smaller I has to move faster to have the same kinetic energy as the one with a larger rotational inertia. And the other way to think of it is, yeah, it's easier to get it rolling from the start. The one with the bigger I is harder to get rolling to begin with. Good. Two ways of thinking about it. All right. And let's see, one more while I've got this up. We have to do the ice skater demonstration for no, I'm not going to skate for you.
This is a Hoberman sphere. I've rigged mine up with a couple of strings, so I can make it bigger and I can make it smaller. Now I'm going to get it rotating, and I'm going to change the size. Watch what happens to the angular velocity as the size increases and decreases.
Okay. So this is conservation of angular momentum. Okay, we're done with this now. And it's the, you know, when you see the ice skater and they're spinning around, they pull their arms in and they spin really fast and they put their arms out and they spin slowly. Conservation of angular momentum. So in this case, we have L initial has to equal L final. What is L? It's I omega. So if I is small, then omega has to be large. And if I is large, then omega has to be small. That's a visual of the equation there, right? If we make I big, omega has to get smaller. If we make I smaller, omega has to get bigger because the product of I times omega is a constant. Okay. Do we have time for one more problem? Let's see, did we do the disk falling on the other disk? I think I emailed it out. Okay, so this one's rotating. This one is not. And then at the end, they fall on top of each other. We did it in the review session. Okay, so it's posted somewhere. What should we do? Let's do, oh, I know what I wanted to talk about. So these are completely independent of one another. We've got sort of three main tools we use, right? We have energy conservation. We have linear momentum. We have angular momentum. And linear momentum and angular momentum are independent. Let's look at this example. We've got a hockey stick sitting on a sheet of ice, okay? We're looking down, top-down view. Hockey stick on a sheet of ice. So there's no friction. And a puck is coming along. I'll make the puck a little bit smaller. A puck is sliding along the ice with some initial velocity. And it hits the hockey stick. So what happens? It keeps going in a straight line, but it's going slower now, right? And the hockey stick, what's the hockey stick doing? The hockey stick is rotating. And what else is it doing? It's moving, right? And what do we know about this problem? What do we know? We know that linear momentum has to be the same. Yeah, frictionless. We'll make it frictionless. Otherwise, it doesn't work. We know that linear momentum has to be the same. It's a collision. The linear momentum has to be the same. There's no y momentum. If we're calling the horizontal, there's no vertical momentum. So everything's moving horizontally initially. Everything has to be moving horizontally at the end. The hockey stick's not magically going to move up or down the ball if the ball keeps going straight like this. So one thing we know for certain is that linear momentum is conserved. And if it's a sheet of ice, right, because how do we know linear momentum is conserved? There's no net force acting on this system. It's an isolated system, right? And what else do we know? There's also no net torque acting on this system if it's a sheet of ice. So angular momentum is also conserved. And so we would end up with two equations, one from linear momentum, one from angular momentum, and we could solve for two unknowns. Maybe the maybe omega final and v stick if we knew v initial and v final for the puck, something like that. We could solve for two unknowns. And sometimes we have angular momentum conserved when linear momentum is not, right? Like if something is attached to the Earth. If something is attached to the Earth and something hits it, linear momentum is not going to be conserved because the Earth is holding on to that. The Earth is holding on to that rod right there, and it's not letting it move to the right. It's letting it swing a little bit, right? But it's not letting it really move to the right. So the initial, so in this case, we cannot use linear momentum, but we can use angular momentum because it's free to rotate about that point. The net torque is zero at that instant if we don't wait too long. If we wait too long and gravity starts to act on it, then we can't use this one either, right? But if we just look at an instant before and after the collision, we can use angular momentum. Yeah, it doesn't matter if the ball attaches to the rod or not. If the ball bounces back, it's still the same situation. The rod's linear momentum is impeded by the fact that it's attached to the Earth. Okay. So what did I say? 3:30 today, I'll log in, use the normal 4 o'clock office hour login, and then I'll send out an email if I can try to do a later one. I'll do that. All right, I'm going to stop the recording. And yeah, I can try to record. Yeah, I'll try to record the review session, but I will definitely post the notes. So any problems we work, you'll get a nice solution posted in the section there. I will stop this, but I'll stick around if there are questions now. I can stick around for a few minutes.